Great. Well, we will warmly welcome Hussein Mozanar, who is a PhD student at MIT, advised by David Sontag. His research focuses on using AI to help people complete tasks more efficiently. Please go ahead.
All right, thank you, Sergi. Welcome, everyone. So yeah, I'm Hussein, I'm a PhD candidate at MIT. And today I'm going to talk about training human AI teams. And please feel free to interrupt me with questions. I'll try to monitor the chat. If there's a question on chat, please let me know, Sergi, and I can try to answer it on the spot. And I'll try to leave a few minutes at the end for questions.
Okay.
All right, so let's get started. My vision is that in the very near future, almost most of the decisions we take, or even actions, will be either assisted or performed by an AI agent. And this is already starting to happen in a lot of domains. So in particular, AI is being used to assist radiologists for breast cancer detection, among other radiology tasks. Large language models are really changing the way we write code, with popular products like GitHub Copilot being used to assist programmers inside their integrated editors. And this is really a major shift in how humans perform their works. And my goal as a researcher is to try to maximize AI's benefit to humans. And the way I try to do this is by modeling the human and the AI as a team, as a single entity, and try to directly optimize for performance. So we want to think of the human and the AI not as two separate things, but as a single team, and then optimize directly for that performance. So to drive home this point, really the main motivation behind this is that there's a fundamental mismatch in the way we optimize AI models and how they are deployed currently. So this bar is showing you the level of current human AI performance, the level of this team at making decisions. And really the current state is only very optimizing the potential only halfway through. And this is because the way AI models are trained and integrated is without considering that there's a human in that loop. And this causes many failure points, including things like over-reliance or under-reliance. So not properly using the AI to its current full ability. And to really bridge that gap and get that potential that's left for us to optimize, we really need to train the team with this human AI performance objective directly. So to make this things more concrete, I'm going to draw things in a figure. So I have a human, and they're performing their work on the computer. I can train an AI model that is with the objective of mimicking the human on their task. This AI model can be used to provide suggestions to the human, and these suggestions can get displayed directly in the human's interface. So again, this human AI team is this integration of the human, the AI, and the interface in which they communicate with them. And this clearly presents three opportunities to optimize this team: the interface, the human, and the AI. So in this talk, I'll talk about three opportunities to optimize the human AI team. The first one being is how can we train the interface and adapt it from feedback of the human interacting with the model. The second opportunity is training the human itself to better know how to interact with the AI model, to make sure that the human's mental model of the AI is accurate. And the third opportunity is training AI models that complement rather than mimic human behavior. And this talk is going to focus on all of these three things. So just as a helpful outline of today, we're going to talk about these three directions. And for reference, each of these directions is based on the following papers published in machine learning and HCI conferences. So let's start with the first part of our talk, which is going to be about adapting interfaces from human feedback. The main tool I'm going to use today is modeling the interaction explicitly. So to make any progress, we need a model of how the human is interacting with AI. Once we have that model of the interaction, we can figure out what's wrong and use that model as a basis to design interventions to improve the inefficiencies. So explicitly, our approach is going to be to build a taxonomy, a set of different human activities where the human is interacting with the AI. Once we have that taxonomy, that list of states, we can model the human as kind of a stochastic process over these states. And that's going to enable us to find out what's going wrong and try to fix things. And we're going to use a concrete application to illustrate this approach. So specifically, I'm going to focus on GitHub Copilot. So Copilot is a large language model that's integrated into your code editor. And at each moment in time in which you stop writing code, Copilot is going to show you a suggestion that's going to be engraved. And you can accept that suggestion into your code by pressing Tab, or reject it by continuing to write code or pressing the escape key. And Copilot really is one of the most used LLM software as of now, and I think one of the most useful softwares. And it's really used by millions of programmers on a daily basis. The first burning question is Copilot useful? And one of the best evidence for this comes from the Copilot team itself. And they found with a randomized control trial that programmers writing code with Copilot versus without are 55% faster. And really, all of the state of AI development right now is about making models bigger and larger. And we think that by making these models bigger, hopefully we can improve human productivity. So to try to investigate that question of, if we keep making the AI larger, where are we heading? I ran my own study with collaborators at CMU, where we built our own version of Copilot. But instead of using the GPT-3 model, we swapped in the LLM with 3 different models of increasing capabilities. So the first one is called Llama 7 billion, the second is called Llama 34 billion, and the third is GPT 3.5. Now, Code Llama 34 billion is much better at all of these static benchmarks like human eval than Code Llama 7b and GPT 3.5 as well. So these are models of increasing size and abilities on these programming benchmarks. But once we try to understand how humans are interacting with these models, for example, we find that with Code Llama 7b, people are only 7.5 faster versus no AI at all. Then with Code Llama 34b, people are 90% faster than without AI. But once you move to this much bigger model, hypothetically much bigger model, but at least much better performing at all of these benchmarks, you don't get any improvement in terms of human productivity. So really, even if GPT 3.5 is twice as good at these benchmarks, it's really not much helpful to humans. So maybe the path right now is not to optimize the AI to be as good as it can on its own, but rather thinking about this human AI team and optimizing for that performance. And we might have better opportunities to improve human productivity there. So now the question is, how can we improve Copilot without improving the AI model? So again, to do this, we need to understand how people are using it and try to build that taxonomy I alluded to. So to understand this use, I'm going to play for you a video here on the left of me trying to call a holistic regression function. And on the right, I'm going to try to track my behavior with a state diagram. So now as the video starts playing on the left, I'm writing code, and I'm trying to write code for a holistic regression function. So I'm in the purple state, writing new code, new functionality. As I'm writing, Copilot is interrupting me and showing me a suggestion. But once it shows me the suggestion, I'm not thinking about the suggestion it's showing me. I'm still thinking what I want my function signature to be. So I transition to this state of thinking about code I want to write, and I quickly reject that suggestion and go back to writing my function signature. And once I finish writing my function signature, Copilot is now going to show me a suggestion. But here, clearly, it's not useful at all. It's just an empty suggestion. And so I'm going to verify it and see that's not useful for me, and then reject it. And then I'm going to try to explicitly write a prompt telling Copilot that, oh, I want you to initialize the weight and biases parameters of the model. So I transition to this purple state of prompt crafting. After I write my prompt, I'm going to go back and verify the suggestion. And here in this setting, I'm going to accept it. And then I'm going to go in this loop of waiting for suggestions, verifying them, and accepting them, as I'll show in the video. So here I get this. So kind of a sequence of accepts that I perform until there comes a point where I don't like the suggestion. So I'm going to go back to writing a prompt. And then Copilot is going to show me a huge suggestion. And it's basically the optimization loop of the code. However, it's too long for me to quickly verify. So what I will do is I'm going to defer my verification for later. I'm going to accept the suggestion without verifying it. After I accept it, I'm going to go ahead and verify it. Kind of, you can see my cursor line by line going through it and seeing if there's something I don't like and then editing it. So kind of this video really tries to show you how people are behaving with Copilot. And there's many insights that we're going to try to more formally describe. For instance, the fact that I accepted or rejected suggestion is not an indication of my preference for that suggestion. It depends also on my latent state. What was I thinking? What was I doing when I was shown that suggestion? And you can also see the different types of activities that I'm doing when I'm coding. So to formalize these insights in a more structured manner, we derived this taxonomy, which we called CUPS, short for Copilot User Programming States. And really think of it as a profiler for the interaction. So it consists of these 12 unique latent states that include things that I just showed you, like verifying suggestions on the top, prompt crafting in purple in the kind of bottom right, editing suggestions, and kind of my favorite state, the not thinking state. And so really to better understand behavior, we collected data of 21 programmers at Microsoft. So they write code for a given task. Then they try to self-label their coding session, as we did in the exercise just previously, with these cup states. So they have their video of their coding, and they label fragments of that interaction with what cup state is most appropriate. And that gives us data of labeled coding sessions with their according cups labels. And perhaps the biggest insight we can derive from this is understanding where do programmers spend their time. So on this graph I'm showing you on the left, for each of the 12 unique cup states, and I'm highlighting in light green those which are Copilot interaction states, like verifying suggestions, editing suggestions, prompt crafting, the fraction of a coding session that is spent in that state. So you can see kind of the top state is that of verifying suggestion. So almost 22% of your time coding with Copilot and that user study is just verifying the suggestions that you get shown. It's not surprising to see that the second most common state is writing code, and the third most common state is thinking about what you want to write. And so it's kind of a really change in the type of activities that we're performing and the amount of time we're spending doing them. Once we dug deeper into this data, we also found that programmers only accepted 21% of suggestions. So if you do this rough calculus, you have 22% of your time going into verifying suggestions, and that time goes into 80% of suggestions that get rejected. And so if I multiply these two numbers together, I can get the time that's spent verifying rejected suggestions. And that's at most probably time that's going to waste, but because it's going into verifying stuff that you never use inside your code. You may argue that sometimes people reject suggestions, but can still gain value from them. And that's why I'm saying it's at most that time. Please feel free to interrupt me since we're a small group with questions at any time, and I'm happy to answer. And so now, given this number, we can clearly see there's an inefficiency in the interaction. And how can we remedy this? Well, the main design decision in building a system like Copilot is when do you interrupt the user and show a suggestion. It's basically Copilot is a large language model, and on top of it should be this logic of when do you optimally interrupt the user. And intuitively, the way you would design this is as follows. You want to see if showing the suggestion would help the user in completing whatever task they're doing faster. So if I denote by the function t, the time to complete the task, and I try to figure out what's the time to complete the task if the suggestion was not shown versus if the suggestion was shown. And if I take this difference and compare it to some threshold tau, that's going to give me a way to control when suggestions are shown in a very fundamental manner. So to illustrate this, let's see two extremes of setting this threshold tau. If I set tau to -infinity, that means I don't care if the suggestion helps you in the task, I'm still going to show it. So basically, this equation is always showing a suggestion. And you can clearly see on this video, you get this very annoying interaction where the model is constantly interrupting you. And so that's not how you want to design this. Let's see the other extreme, where you set tau equal to 0. Basically, you only show a suggestion if it reduces the time for you to code. And here, Copilot is going to wait for me to write my function signature. And only after I'm done writing that function signature, it's going to go ahead and interrupt me with a suggestion. And in theory, that should have a higher probability of me using that suggestion and being useful for me. So how do we design an interface that then can accomplish this? Unfortunately, if you really want to estimate that time difference if something was shown, this is really a counterfactual estimation problem. And you need counterfactual estimators, and you need a lot of this COPS data that tells you about the time that people, users take, and really requires tons of that data. So instead, we're going to think about a slightly different design decision, which is to consider the probability of the user accepting a suggestion given supposing if it was shown. And the way I'm going to motivate this is as follows. If you assume that you only gain value from the suggestion if you accept it, then a necessary condition for it to be useful is for you to accept it. So if you show suggestions that have a high probability of acceptance, user accepting them, then hopefully they're going to be useful to the user. So we're going to try to build an estimator of, given the suggestion, given the context that the user is in, the code they've written, how long they've been writing code for, their probability of accepting a certain suggestion S, and comparing that to a threshold tau. Now, how do we build such an estimator? Well, what we're going to do is we're going to collect a lot of raw telemetry data from 500 Microsoft users. And that's going to total about 5,000 coding sessions with 200K suggestions. And for each suggestion that appears in the data, we're going to extract features about the suggestion itself. So its length, the number of lines that suggestion, an embedding of that suggestion, features about the prompt that's shown in blue. So how long was the prompt, occurrence of certain keywords and embedding, and features about the suggestion, the session itself. So, the file you're writing code in. What were your previous 5 actions? So that's shown in green. And I'm going to take all of these features, concatenate them, and I'm going to feed them into an XGBoost model that's trained on this binary signal of accept and reject. And so what we can show is that with this model, we can achieve that interface intervention where we can selectively figure out which suggestion we want to show and which we want to hide. And so in particular, we can hide 30% of suggestions that were shown in a retrospective evaluation and guarantee that 95% of them would have been rejected if they were shown. So on this graph on the right, I'm showing you as I vary the parameter tau, On the y-axis, I'm showing you how many of the suggestions I can hide. And for each parameter setting tau, I know how many of those that I hid were actually rejected or not. So if I set tau to be a very high value, I'm going to go to the bottom right, where I'm going to hide a small fraction of these suggestions, but I'm going to guarantee that most of them would have been rejected if they were shown. And so this was work that I did at Microsoft, which owns GitHub, and it got implemented in Copilot in lightweight version. And the specific setting of that parameter enabled them to eliminate 4.5% of suggestions, and almost most of them would have gotten rejected. So really the takeaways here is that we can understand the interaction by building this taxonomy of states, and it allows us to identify inefficiencies. And we can use this feedback data of the interaction to fix these inefficiencies. So that kind of concludes the first part of my talk. And now we're going to try to transition to understanding how do people know how to interact with the model. Basically, how do the users even know when to accept the suggestion? That's kind of something we skipped over. How do they know when to accept the suggestion or reject the suggestion?
Can I ask a quick question
Yes.
about the first part?
Yes.
You had something about prompt writing as one of your categories.
Yes.
Did you measure prompt rewriting? When you get a suggestion, you don't like it, you rewrite the prompt. I do that a lot myself. That's also a kind of waste of time.
Yeah, that's a great question. So we have in our paper kind of these sequences of behaviors that people do. And one of the most prominent ones is this kind of loop of you write a prompt, you get a suggestion, you don't like it, you go back to prompt crafting, you verify, and then you don't like it, and you kind of keep iterating. And so we do identify that as like a sequence of states, right? So kind of look at n-grams of states. And what we show in kind of one of the papers that sometimes when you go through this effort of writing prompt, writing prompt, you almost surely eventually accept something. Maybe not because it's useful, but because you spend all that effort writing your prompt.
So one of the challenges here is if you, let's say your model correctly identifies that a certain prompt I wrote, I'm very likely to reject the output. Then you don't show the output, so I can't rewrite my prompt anymore. So you have these counterfactual cascading effects. How do you deal with that?
That's super interesting question. So here we're now thinking about this game of, you know how initially the model behaves to you. And if I built my estimator correctly, I should know that whenever you rewrite your prompt, that you want a suggestion to be shown. So that's kind of a limitation of this approach, where if you only look at what gets accepted, then that's not the correct optimization. If you also had another signal that says, this is when people request suggestions, then you should also incorporate that into the model. But eventually, I think that specific case you have where people are requesting, there is a shortcut in Copilot where you can just request a suggestion. And so that, in theory, should fix it in the short term. But in long term, we need something better than just predicting acceptance and using these signals like the state you were in to know when you display a suggestion. Does that make a bit of sense?
It does. I mean, I use that shortcut myself. It's just it's like a last resort. I'm like, where is it? Where's my thing? And then
exactly. So that's why just using that signal is not good enough. You need that insight of what was the user state to know when to make these decisions.
Thanks.
All right. So now we're going to transition into a slightly different setting of AI-assisted decision-making instead of Copilot. And so in this setting, AI is going to provide an answer, and the human is making a one-shot decision of either using the AI's answer or making the diagnosis of their own. So here I have a chest X-ray, and the human can make an immediate diagnosis of saying this patient is healthy or has pneumonia, and the AI is making a prediction that the patient is healthy and providing a confidence score. And there's a button that says you can use the AI answer. And basically, how does the user know when to use this button or not? First, I'm going to show you a figure that's adapted from Christoph Gauss. And it's going to show you what would a word look like where the user knows exactly when to rely on the AI and when not to. So suppose I have the human at this level of accuracy. Suppose the AI is surpassing that level. You would expect if I put the human and the AI together to get something that's better. That's what a world would look like, where the human knows exactly when to rely on the AI. But I think maybe as many of you are familiar, that's not often what happens in reality. We often get situations where this human AI team is performing worse than the best of the human or the AI. And one of the most recent examples of this is in a study by Agrawal et al., where they had radiologists predicting with and without the AI. And even though the AI model was better than 2/3 of these radiologists performance did not increase when you gave them the AI model. So even if all radiologists used the AI, they would have done better. They were not doing that. And it was not the case that they were never using it. They were just using it in suboptimal ways in different settings. And this has sadly even become a conjecture in the literature, with people stating things like the performance of the human AI team is worse than the maximum of the AI or the human. And really what I want to try to see is how I can flip that inequality. How can I ensure that the human AI team is better than either they are the human? And the way we're going to do this is not by optimizing the AI, because we know the AI is maybe better than the human. It's by optimizing the human here and trying to teach them when you should and when you should not rely on the AI. Ideally, what I want to create is a set of natural language rules that describe how should the person interact with the AI. And once I've created these rules, I can teach them to the person. And hopefully the person is convinced of them. And they can use these rules in the future and kind of update their mental model and appropriately rely on the AI. So how can we get to a stage where we have these natural language rules, which are nicely written for the human? So concretely, I'm going to consider a very mirror task to the radiology, but where basically I'm asking people, is there a traffic light in this picture? And the picture is very blurry. And so it's kind of very hard for people and for the AI. And the AI is going to provide, a bounding box if it sees where the traffic light is. And it's also going to give them a confidence score. So concretely, I'm going to formalize things. I'm going to formalize this decision of the human to rely on or not to rely on the AI by this function I call integrator. So this is the human's mental model. So function R takes as input X, the image, and A, which is the AI's suggestion. So in that traffic light setting, it's going to be, yes, there is a traffic light with this % probability. And the human can either decide two things. Either they ignore the AI or they use the AI's answer. So either 0 or 1. And so this is kind of an abstraction. And here I'm going to make an assumption of how this function looks like, how the mental model of the human looks like. I'm going to assume it decomposes into a prior, R subscript 0. And this prior mental model can be arbitrary. So suppose, the human always relied on the AI or always ignored the AI. So it can take arbitrary shape on each simple example. And I'm going to assume as the human observes data, as they kind of interact with the model, they're going to update their prior. So they're going to have a posterior. It's going to consist of local updates in around points that they observe in an embedding space. So kind of suppose the human sees this specific example 0 as a specific with specific input and specific AI suggestion. And here they figure out that I should ignore the AI model on this specific example. And so kind of they update that prior in a local region around this point they observed. And okay, then in this region, I'm going to ignore the AI. And as they observe more points, they're going to patch their prior with the data they're learning. And so basically, my goal is to get the human's integrator and shape their posterior to a better end outcome. So the way I will do this is I'm going to first try to understand what would an optimal human do. How would they optimally rely on the AI. So I'm going to assume I have a data set of examples, and I'm going to try to label each point in my data set with a 0 or 1, whether the human should rely or ignore the AI on this specific example. So I have my data set. I've labeled it with the optimal decision that a theoretical human should make. And basically, onboarding is going to train this person to follow what the optimal integrator would do. And so kind of the first step, if you want to teach someone, you want to understand where they're starting from, their prior. And so here I'm just going to assume in this figure that the human's prior is to always trust the AI. So they would label all the points in this figure as a 1. And clearly, there's 2 regions where the human makes mistakes. So this cluster of 0 on the top right and this cluster of 0 on the bottom right. And now I've identified these 2 clusters. So we have a kind of a discovery algorithm to find these clusters. And I really want to say is like, human, look at these 2 clusters. You're making mistakes. You should ignore the eye on these regions. And kind of the way I'm going to communicate that to them is by describing these clusters. So we're going to take each of these regions where the human collaborates incorrectly with the AI and describe them with a natural language rule. So I'm going to assume each example can be described individually. And my problem is to go from single descriptions to describing a region. If I want to describe a region of points, it's not enough to describe what's inside the region, because I have to figure out where does the region start and stop. I have to figure out its boundary. So I need to contrast what's inside the region versus what's outside the region. So what I'm going to do is I'm going to take a random sampling of points from inside the region, so the set S plus, and a sampling from outside, the set S minus. And I'm going to ask a language model to contrast these 2 sets. And I'm going to come up with a description. So that's my initial description. This region consists of highways during the night. But because the language model cannot fit all of the points in the region and what's outside in its context, I need the clever way to select that set S plus and S minus that's not just random. So my procedure is going to be iterative. I'm going to start with something random, and then I'm going to continuously improve on it. And the way I'm going to do this is as follows. I'm going to take this initial description, so this description in gold. I'm going to plug it into my embedding space. Once I plug it into my embedding space, I can try to find counterexamples to that description. So that region description should match everything inside and should not match everything outside. And so in theory, if there's a point outside the region that has very close embedding similarity with it, I should ask the model to make sure to contrast to that point. So that point in red I'm showing you. And if there's a point inside the region, but that has very low similarity with that description, I should tell the model to make sure to describe that point in particular. So that point in green. And so I can add these 2 points to my sets and then ask the model to describe again. So I get a better description that's better refined. So now actually the region is highway during night, but without cars. And I can keep doing this iterative procedure until I reach the maximum of my context length. And so we have one synthetic experiment that I'm showing you here with the dataset MS Coco. So a dataset of images and captions. And there's objects in that dataset from over 100 classes. And I'm going to try to describe each class on its own. So for example, I want to describe the set of points that have set of examples that have an apple inside of them. Usually the scenes that contain an apple also contain an orange. But really the description I want to find is apple exactly. So that's my metric. I have the description, which is apple. I want to find that exact description of the region. And so here I'm showing you the Rouge metric for captioning. If I don't do any contrasting, I get 25%. If I add contrasting, I'm at 32%. If I cleverly select the examples, not just randomly, but with this counter examples, I can boost performance furthermore by 3%. We now have this clever procedure to figure out how to describe regions by cleverly selecting which points should the model pay attention to. So at this point, we have our regions, and each region has a description, and we have points from each of these regions. What's left is to teach them to the person. And so the way we're going to teach these guidelines is we're going to take an example from each region, show it to the person. The person's going to make a prediction on that example. Then we're going to tell them if they were right or wrong, and what should have been their decision on that example, and what's the description of this region. So we're going to take an example and help them generalize from example to region. And so we have kind of these guidelines that we've created. And so we did a user study on that object detection, traffic light detection task, where some people received onboarding and some people did not in a random manner. So back to kind of these initial figures I was showing you, we can benchmark human performance without AI. We can benchmark AI performance, and it's kind of at the same level of the human at 79%-ish. The human augmented with the AI's advice, but without onboarding, is at 77%. So it does not exceed the human or the AI alone. But now, once you do onboarding, you can boost the performance of the human by 5 percentage points. And that increases statistically significant. And it's not only because of exposure to the task, because in the control, we also have the human interact with the model before we test them. So it's really because of these rules that they've learned in this onboarding phase. And so kind of the takeaways here is that we can train the human when to trust the AI via these natural language rules and can improve their performance.
Can I ask another question here?
If
So you said in the control, the human got to interact with the AI.
Yes.
So they would just get predictions and then tell them if they were right or wrong, and it was random effectively.
Yeah. So I expose them to the same number of examples, but without telling them the region descriptions. So I have them, practice in the beginning, but these examples are chosen randomly. We also have a baseline where they're chosen a bit more smartly with kind of a lime way of choosing examples, to describe the AI's errors, and that's still not sufficient.
Okay, thanks.
One related question. An alternative to the named regions would be to give the human some kind of black box predictor of when it ought to trust the AI more than it normally would, or or less, with no interpretation, just like this kind of image for some reason that's opaque is one where you should trust the AI more or less. Do you think that would work?
Great question. So we had another arm in this study where we did something very similar to what you were mentioning, but we also gave a reason why. So we would tell them, the users, don't trust the AI, and because the AI is observed to behave badly on those examples. And what we found is that did not help at all. So that users took more time to make decision, and they didn't do better than just without that recommendation. And I think there were two reasons for that, which I'm making a hypothesis about, is that you're just confusing people. Like, you're showing them the AI, and then you're telling them, oh, don't trust the AI. And so you're making them doubt themselves and doubt, what the AI, so they're just more confused. So that's my primary, I think, reason why this didn't work in that specific experiment. We did another task where we had, it was a different study where we had a question answering task. So you have a question, multiple choice answers, and you had GPT 3.5 tell you what the right answer was. Once you enable GPT 3.5 to not just tell you its answer, but explain it, often what GPT will tell you, it will give you a reasoning for its explanation, and it would also tell you, I don't know how to answer this question. So basically the model refuses to answer the question, and by enabling the model to tell you itself that I don't know how to answer, that enables you to know when to trust it better, because you can verify that the model doesn't know what it's talking about, because once you ask it to verify, it tells you I don't know. And so that mitigated any improvement due to onboarding. Now, what's the difference between that setting of question answering versus the object detection? In question answering, you can verify the explanation from the AI easily, at least when it tells you, I don't know how to answer. You just know not to trust it. In the object detection setting, often the AI will give you like a bounding box, okay? But you can't verify the bounding box either because it's too blurry for you to figure out. So you cannot easily verify the explanation of the AI. And so that's why, these recommendations were not as helpful, because they were not easily verifiable and just confused the user. So a better maybe interface that would work is just, either hide or show the AI's answer based on that prediction. Does that make a bit of sense?
Yes, it does. Thanks.
So let's take what Doug suggested even further. And that's going to be the next part of my talk. So what if, the human didn't have much time to look at all the examples? And that happens a lot in content moderation or healthcare triage. Can we still get a team that's better than either the AI or the human? So can we still get an effective human AI team? So the way we're going to do things now in this final part of the talk is with something I call a deferral system. It's going to be very much analogous to before, but now AI is going to make decisions on our behalf. So suppose we have our input X, our chest X-ray here. We're going to build an AI model that's going to be called the rejector, R of X. On each example, this rejector is going to make a decision. Either this patient should be routed to the radiologist, H of Z. So the rejector would say, oh, this person should go to the human. It's going to defer that person to the human. Or this rejector is going to say, actually, let my classifier predict. So my classifier, M of X, is going to make a decision. And it's going to make a final decision, Y, and it's going to compare that to a ground truth. So here, the rejector is analogous to that integrator, but here it's AI making the decision. So for each patient X, they're only seen by either the radiologist or the classifier. So now we kind of have this similar intervention that I mentioned before, but now the human doesn't even see the example. The AI just makes a decision on their behalf. And kind of how do we build such a system where we have this optimal delegation and we have that classifier? So I'm going to assume I have data that's a tuple of the following. We have the input X, the human's prediction H, and the ground truth label Y. And I want to optimize the loss function, this loss of deferral of function of the classifier M, rejector R. And it's going to compare what's the output of the system to a ground truth label Y. So if R is 1, it's going to be H. If R is 0, it's going to be M, and compare that to a ground truth label Y. The naive way to learn such a system is to train your classifier ignoring the human, so as you do in machine learning. And then for knowing when to defer, threshold the confidence of that classifier to a threshold tau, and say when that model has low confidence, let the human predict. And there's two, suboptimalities in this approach. One is that the rejector does not consider what the human confidence is. So even though your model might have low confidence, the human might have lower confidence, and so you're not considering that. So that's been pointed out by Raghu et al. The second suboptimal thing is that the model does not adapt to the fact that it's only making prediction on a subset of the data. Since it's making prediction on only a subset, it should optimize its performance for the set of which the human is not very good at. So it should adapt to human weaknesses. And so kind of to fix both of these things, we need to jointly learn how to classify and defer. I'm going to go over this a bit quickly. But basically, if you were just going to take this objective function and optimize it, it would be computationally hard, even in the simplest setting you consider. And that's not the same, and that's kind of the setting where if you were doing just classification, you could do it in polynomial time. But if you're doing now joint learning, it becomes computationally hard. So now how do I practically learn such a system? And the way I'm going to consider this problem is as follows. Instead of making a two-stage decision of defer, classify, I'm going to make a one-stage decision of either predict class 1, class 2, class 3, or defer. So I'm adding this extra class, and I'm going to call it defer. This is an instance of a more general problem called cost-sensitive learning, where for each input example I have a vector of costs for each class I'm considering. And basically, the goal is to pick the class with the lowest cost. So in the language of deferral, pick whether it's less costly for the classifier to predict or the human to predict. And at a high level, we show that any algorithm for cost-sensitive classification, I can transform it into an algorithm for learning to defer and guarantee that minimize the objective we care about. So basically, you take your standard machine learning setup, you have a neural network, and it has C output heads for C classes. It's trained with cost entropy loss. I can transform it by adding one more output head, swapping out cross entropy loss for the learning to defer cross entropy loss. And now I have a machine learning model that's human aware, can defer optimally. And kind of very quickly, in experimental evaluation on these chest X-ray data sets, we can show that by using this joint learning approach, so this kind of last column, we can get better accuracy than these previous baselines and better than the radiologists or the AI on their own by only using the human 50% of the time. And so kind of the takeaway here is that incorporating the human into the machine learning process can really improve downstream performance. In these last 2 minutes, I'm going to go over future directions and we can chat more about them. And really all my future research is going to focus how can we enable AI to help us make decisions every day. And the first problem is about dynamics, how the AI should adapt from the human's feedback. So I previously spoke about these myopic signals like accepting suggestions. Can we think about other feedback signals that can tell us what longer term outcomes? The other side of the coin is humans adapting as the AI improves. So again, how do we ensure that their mental model is up to date? So kind of this is a game between the human and the AI as they evolve over time. The other side of things is about the interaction mechanism. And so there's 3 opportunities that I want to explore. First is AI that automatically steps in when it knows it's helpful. The second is allowing the AI to figure out what's the human's intent without them explicitly writing down a long text that tells the AI what they want to do. And enabling the human to control the generations with kind of these nice knobs instead of just text. And I think this leads to a vision of developing, agents that take actions rather than just advice. And how do we build such agents? And how do we build groups of these agents to solve tasks? And kind of the last part is about evaluating, are we on the right track? Is this human AI team, performing well in many domains? I'm going to skip the slide, which might be interesting. And kind of at Semantic Scholar, what I would envision those directions looking like is kind of trying to think of what would the AI assistant for the research process look like. So very similar to Copilot work, how can you think about assistants that maybe have augmented access to APIs, other knowledge bases that automatically step in as you're in the process, multi-agent teams to help you in the writing or review process, and kind of an agent observing you in the research process and making suggestions. And trying to understand how can you incorporate human feedback and even social aspects of research into the model. And kind of even for fun, trying to think about how do we simulate the entire scientific process, with these different AI agents and community. So I'm going to stop here and acknowledge all my collaborators at MIT, MSR, IBM, and CMU. And thank you so much for your time today. Sorry that I went a bit over time.
Let's thank the speaker. Thanks a lot.
Thank you.
I've already asked a bunch of questions. I have more, but if I'd invite other people to step in, please. If you have any questions, we have 8 minutes. Okay, I can kick us off.
Maybe I'll ask one, although I agree with Sergey, it'd be great to hear from other folks. Can you go back to slide 17 really quick?
17. Yes.
Okay, so this curve, I mean, it is good that you can kind of trade off how much you can hide with, you know, that you get better at as you hide less, those are more likely to be rejected. But I guess, you know, this curve doesn't bend that much, right? It's almost diagonal. And so for a lot of problems, you know, you could get like 80% of the reduction in suggestions at, you know, only 20% of the you know, loss of good things. So it's like the 80-20 rule. I'm not sure I totally said that right, but this curve's almost diagonal, right? So it's you know, you're not getting points where you can actually hide 80% of the stuff and get, you know, a much smaller fraction hidden. So I guess, are you happy with this curve, or do you think you could drive up the accuracy of this, or is there some reason why it's especially hard?
So this curve is really, so, you know, it's doing much, much better than randomly hiding stuff. So if I was to draw, like, what would a random line be? It would be horizontal, right?
That's
sorry,
right.
vertical. Yeah, not horizontal, vertical. Basically, if I hide 30%, it would hide. You know, I would still be randomly. So since 21% of suggestions accepted, I would be on this kind of line. So I'm doing significantly better than that. Now, what's the opportunity to improve that curve? The opportunity comes from incorporating the latent state. So, so if, you know, I showed you these different states. If I had these labeled data, which I have for this specific study, I could improve the accuracy of my model significantly better because I know where the user, like if you just went to the bathroom, I know you're not going to accept the suggestion. I could never figure that out because it's just unobservable. So if I had this latent data, then I can significantly improve my model. And we show that in kind of when we're evaluating on this specific subset of the data. So that's the most promising avenue for me, at least. Does that make sense?
Yeah, it does. And it's a good point that you're doing much better than the vertical line. Thanks.
I don't see any hands up, so I guess I'll proceed. Oh, Joseph, please.
Sorry. Can you get a 44?
Yeah.
And great talk, by the way. I really enjoyed it.
Thank you. Yes.
So there's a lot of stuff here that I find very interesting.
Yes.
Specifically about AI being auto-stepping in. So I feel like that's both a machine learning problem and also an HCI problem.
Yes.
Especially when you have either a single user or multiple user with an agent. And then the other one that I was really interested about is this like interpretable knobs for control generation.
Yes.
I guess I just want to hear a little more about each of the two. What your thoughts on?
Yeah.
Explore.
Yeah. So I'm starting to think about this problem of auto stepping in. So Copilot is a way to do that, right? Like but it's a bit more simpler. Now I'm thinking about it with a chat agent. So again, in the context of writing code. So I have my editor that's open and I'm writing code. And I have a chat model that's observing me writing code. Now there's two ways to design that agent that steps in. The first one I'm trying to explore is that I try to predict what question you would have asked. So I have a bunch of data where people, I can see their code and I can see what questions they're asking based on that code. So I can try to predict what question they ask, answer that question, and then I need to figure out if it's useful to show that answer or not. So that's one way to design such a system, right? Another way to design it is to think about, you have this code. I can try to infer what's the task you're solving, and then try to give you the suggestion that gets you as close as possible to solving the task. That's a different way to design such a system. So those are kind of the design choices that I'm trying to think about. And then there's the other angle of like, is it good to interrupt the person or not? And what data can we use to figure out when to optimally interrupt? So that's about the stepping in. That's kind of some concrete stuff I'm thinking about. For the interruptible knobs, that's something I've been trying to think about, but finding it very hard, honestly. So the easiest setting of this is an image generation, where you have a prompt, you get an image. And then sometimes for images, there's very easy ways to control things, like if you ask for an image, that's a blend of two artists, right? You can imagine there's a slider that tells you, oh, you want it to be more like this artist or that artist. And what does it look like for text or code? For code, you can think of it, make it more documented, less documented. But the idea is to create these knobs and on instance basis, not having like prefixes. And how can we get to that vision? So I don't have very concrete ideas, but that's kind of the realm of things I'm thinking about there.
Oh, no, that's great. I would love to chat more. Jonathan?
Thank you, Joseph.
Yeah, I also really enjoyed the talk. I was wondering about the work where you were modeling the internal states of the human, and it seemed like that involved a lot of manual labeling. But it would be cool to be able to deploy agents in like new domains that, without having that step. Just wondering on your thoughts on how to reduce the cost of that.
Yeah, that's a great question. So in that Copilot study, we had people self-label their data because I don't know what their intent is. So they would code, and then we designed like a video labeling tool. And it's kind of easy navigated. There's shortcuts. It's kind of pretty quick to do this for like a 30-minute session. And the hardest thing, which is made easy in Copilot, is there's natural fragments. So there's natural like scenes you need to label, which is basically when does it interrupt you and when something is shown. To make it faster, I had two directions, which is one of them is a decoding problem. So maybe if I have this small data, I can do good job at decoding, maybe not a good job at prediction. And these are two different things, because decoding, I can see the future. And then the other one is using kind of weak labels. So I can develop heuristics, like I fix my taxonomy. I build a set of heuristics for some of the labels, and that labels for me 5% of the data. And then basically I only ask the user, like when after I build my model from weak labels, if there's a segment I'm unsure about. So that can speed up labeling a bit. I'm not sure where else to make it faster. Like we can create keyboard shortcuts for specific things we care about, but that's the realm of things I've considered.
Thanks. Yeah. Also wondering if you could do it without any human labeling at all. But thanks.
Yeah, that would be the weak labels, basically. That heuristics you would develop, but still human somewhere, I guess.
Looks like we're at time here. Well, let's thank the speaker again. Thanks for the excellent talk. Really appreciate it.
Thank you so much.
Thank you, Hussein.